Assalamu alaikum. My name is Aqsa Shafiq, roll number 21TE08. Today we are diving into the fascinating world of digital signal processing right there. In this lab, I have got a bunch of tasks lined up that showcase the magic of digital signal processing and how it plays a crucial role in various applications.
The lab report of DSP Lab Manual 4 Analyzing Discrete Time Linear Time Invariant. In task 1, how would you differentiate between a signal and a system? Explain the key characteristics of each and provide examples to illustrate their roles in the context of signal processing. So a signal is a representation of a physical quantity that varies with time or space. Signal can be classified based on the various criteria such as continuous time signal or discrete time signal. The example of continuous and discrete time signal are analog audio waveforms, and the discrete time signals are digital radio samples reading sensor readings at specific time instance. And a system is a device or mathematical entity that processes an input signal to produce an output signal. It can be physical system or an abstract representation such as mathematical model or an algorithm. And the example of system are physical system and mathematical systems. The key characteristics of signals is amplitude and time, the representation and classification, and the system and the key representation for system is input-output relationships and their properties and their representations. The example of both signal system and output are as shown below. In task number B, how does LTA system plays a crucial role in digital processing system? Considering their mathematical simplicity, adherence, their superposition principle, and efficiency in frequency response analysis. So, LTS system plays a very crucial role in DSP for several reasons, and the reasons are mathematical simplicity, adherence to the superposition principle, and efficiency in frequency response analysis. In mathematical system, LTI systems have straightforward mathematical representation, making them easy to analyze and design. While the adherence of the superposition principle, it states that the response of the linear system to a sum of multiple inputs is equal to the sum of the response of individual inputs. And in efficiency in frequency response analysis in LTI system exhibit a constant frequency response, making it easier to analyze their behavior in the frequency domain. In DSP, these characteristics of LTS system facilitate the design, analysis, and implementation of various signal processing techniques, making them fundamental in the development of digital filters, signal modulation, and other essential DSP applications. In task C, what are the common methods for signal decomposition, specifically focusing on techniques like impulse decomposition, step function responses, even or decomposition, and Fourier analysis? Explore how this method contributes to breaking down signal and the applications. So, number one point is signal decomposition method. The impulse decomposition method. The point is descriptive and its application. The description is the signals can be decomposed into a series of weighted impulses. This involves expressing a signal as a sum of scaled and shifted impulse function. And their application is useful in understanding how a system responds to individual impulses. Number two is step function analysis. The description is signal can be decomposed into step functions representing certain changes in a signal. It involves identifying and analyzing the step response in a signal, and the application commonly used to analyze system behavior over time and understand how system respond to certain changes. Even or decomposition. The description signals can be decomposed into even and odd components. Even components are symmetric, while odd components are antisymmetric with respect to the origin. The application is useful for separating and analysis the symmetrical and asymmetrical aspects of a signal. The Fourier analysis description is signals can be decomposed into a sum of sinusoidal components using Fourier transform. This includes Fourier series for periodic signals and Fourier transform for non-periodic signals, and the application is essential for frequency domain analysis, allowing the representation of signals in terms of their frequency components. The contribution to the signal processing include insight into the system behavior, filter design, modulation and demodulation, and communication systems. In task D, what is convolution? How does it plays a significant role in DSP systems? So convolution is a mathematical operation that combines two functions to produce a third function. In the context of DSP, convolution is often used to describe the relationship between input and output signals of LTI systems. The importance in DSP applications is filtering, signal processing, system analysis, correlation, modulation, demodulation, and signal representation. The task E is, when do we correlate two signals, and what are the key applications or scenarios where signal correlation is crucial in various fields such as communication system, radar and sonar, image processing, biomedical signal processing, control system, wireless communications, and semantic signal processing. So signal correlation is when to correlate signals. Correlation of signal is performed to measure the similarity or degree of association between two signals. So it is typically employed in scenarios where the relationship patterns or synchronization between systems are of interest. Signal correlation is commonly used in comparing signals, pattern recognition, synchronization, and detection of events. While the key applications and scenarios are communication system, radar and sonar, the image processing, biomedical, and control system, semantic signal processing, and their scenarios and applications as shown below. So in the MATLAB, now we'll explain some codes in the MATLAB. The task one is make your own customized function that takes two input signals from user and show convolution sum graphically. So name the function visual convolution. So to get the user input for the first time, x is equals to input, enter the first value of the first signal, for example 1 2 3 and 4 5 and so on, and get user input for the second signal, h is equals to input, enter the value of the second signal. Perform convolution, y is equals to x and h, and create time vectors for input and output signals. Now plot these signals and subplot and give them a title, and adjust the figure layout, display legend, and the output resulting output gives the three signals. The input signal x of n, input signal h of n, convolution result x of n is equals to y of n is equals to x of n multiplied by h of n. In task 2, make your own customized function that takes two signals from the user and use flip and slide method to show convolution sum step by step. So create a function named step by step convolution, get the user input for the first signal, get the user input for the second signal, h is equals to input, enter the values of the second signal, initialize the result vector, y is equals to 0 1 length x plus length h minus 1, flip the second signal, h flip is equals to flip h, and perform the convolution step by step, and the resulting output is this is the final convolution result. In step 3, compute the response of the following system of the input h of n is given and x of s is given, and build a function for this example. For example, four arguments will be passed. Number 1 is input x of n, information about its origin, impulse response h of n, and information about its origin. So it gives the information of h of n and information of x of n. And so in MATLAB code, uh, give the function x is equals to s, it is given below in the question, and give the value of h and x, and perform its output, and the resulting output is this. This is the response of the system of the signal x of n. In task 4, we have the impulse function of the system as n is equals to the value, and x of n is 1 minus 2, and this is the value, and find y of n. If we feed shifted version of the input signal x of n is equals to this, and to the sum we kind of output we receive. So give the impulse response h of n and input signal x of n as given in the question. Compute the convolution y of n, plot the signals x of n, subplot and stem, and give them a title, label, x-axis, y-axis, and plot the impulse response h of n, subplot, stem, give them title and label, and this. The plot the convolution y of n, display the legend, and adjust the figure layout, and three resulting convolutions is shown. Input signal x of n, impulse response h of n, and convolution signal y of n. So this is my lab report of DSP, and thank you so much for watching my video.